get started. So we're very happy to have Boris Bukh visiting from Carnegie, and he's going to talk to us about Bipartite Turan.
Thank you very much. Thanks for coming. This is going to be a bit of an overview talk because it's not meant for the experts. Do not be shy, ask questions. If something is not clear, whether the right or what I say, make some kind of motion, jump.
Do we have to do that?
No, but you can. So again, I'm combinatorialist, which means I deal with discrete things. I'm extremely combinatorialist, which means I prove inequalities about them. What I want to tell you about is a class of problems which are fairly central to the subject, and also I like them very much. So I will tell you what's known, some old results, some new results, and look at them. Okay, so let's start. What is this whole thing? So it's about graphs. So okay, I'm interested in making graphs big, in the sense of number of edges. So E of G is going to be number of edges in the graph G. And what's the game in here is that I have some forbidden graph F. So F is going to be a fixed graph. We're going to see various examples of these graphs in our problem talk. You should think about something very small and simple, maybe a triangle, maybe four cycles, or maybe something like something more complicated. But again, small fixed thing. That's what you should keep in mind. And what I'm interested in is how large can I make a graph so that it doesn't contain a copy of this fixed forbidden graph. So I'm interested in maximizing the number of edges in a graph G which has no copies of F. So when I say copy, I mean I cannot remove vertices and edges from G to get this fixed graph F. So that's what I mean. So for example, let's just explain an example. So when I say copy, for example, this four cycle is I consider to be a subgraph of this graph. So it's not for experts, this is not an induced copy. Or maybe it's making an example more extreme or something. Okay, that's what I mean by that. So I'm trying to maximize over all graphs, again, of some fixed size. Again, of course, if I start maximizing, it will take larger and larger graphs. It's not hard. And okay, so this is the quantity I will talk about throughout this talk. It's denoted normally the subject by x and of f. X stands for extremal function, but actually it is called Turan number because Paul Turan was the first who systematically investigated this. So these kind of problems arise first of all by themselves every now and then in combinatorics, computer science. But more importantly,
I don't understand.
Yes.
I don't understand because the max is n.
No. Max is not n. So if I just have no restriction on the graph at all, so just forget about this one, then the largest number of edges the graph can have, on n vertices have is n choose 2. Right? There are n vertices, and there are for each pair I can put an edge. But if I do that, there will be, for example, I will definitely have a copy of any of this if n is bigger than 3 or 4. So question is, how do I remove as few edges?
You want to know how big can n be so the full graph doesn't have f?
Yes.
No, you fix n.
Huh?
You fix n. You fix the number of vertices. And you ask how many edges can your graph have without having a triangle?
Yes.
So in your question there, you're not
Okay,
considering
got it.
No, it's a graph. It's a graph.
Got it.
It's a graph. It's not a multi-graph again. So between every two vertices, there can be at most one edge. There's no direction to it. It's just is there edge or is there not? Okay, thanks for asking. Okay, so let's look at the simplest case of triangle. Okay, so just so that we are on the same blackboard. So the answer for triangle, this is an old result of Mantel, predating Turan, but which it says this. Okay, it's a number. There is not much meaning in number. Numbers themselves are meaningless. Let me tell you what the meaning of this number is. So the picture which goes to this number is this. So the best graph, the one with the most edges, and still not containing a triangle, is complete bipartite graph. So it looks as follows. It's got two parts, which are equally large. So n over 2 vertices each. Okay. Well, n might be odd. So if it's odd, we make it as close to be equally possible as possible. So I will write probably the only time in this talk actual floor and the ceiling. But later I will ignore those details. And we just put all the possible edges between the left part and the right part, and no edges within those parts. So this is how a graph looks like. That answers your question. And again, it's not a totally trivial, but not a terribly difficult result. That this is the largest number of edges you can. This graph does have the largest number of edges while not having triangles, and actually it's a unique graph. Okay, but anyways, there are more refined results than that. But this is what I want to say for now.
Right.
Good. Now, there is a.
What about the square?
Huh?
What about the square?
Square will be. I'll talk about square now, but before square, let me tell you about every graph, and then I'll specialize with square. So there is a very nice result by Ordish and Stony from 46. Which gives the answer for every graph. So here it is. Again, I'll write the formula down and explain what the meaning is. So the formula is this. Okay, so first of all, what's chi? Chi of f.
What's F?
F is a fixed coordinate.
Oh, chi of F, sorry.
F is a graph per bit.
Okay.
So and again, so this formula you should read. This is little of 1, so this is a asymptotic result. And
Let me write that a little bit.
it's meant to be little of 1.
Very small.
It's a very small little of 1.
Very small little.
Yeah. So this is asymptotic as n goes to infinity. So you should think about f being fixed, like a triangle maybe, or something more complicated. And n goes to infinity. So this is in that sense that little law of 1 goes to 0.
Do you allow loops in your graphs?
No. Again, f hold up, it's a graph. Graphs with no loops, no multiple edges, just graphs. Again, everything I'm telling you has some various generalizations to more complicated contexts, and actually it's usually those generalizations which are useful. But again, I'm talking about the purest form of the problems.
So you were going to say what this chi is?
Yes, thank you. So chi is the chromatic number of f, which is the smallest number of colors, needed to color vertices of G, so that no edge is monochromatic. No edge is monochromatic. Okay. So now
G is F?
number of sorry, so it was chi. Thank you. Thank you very much. So let me just maybe explain, okay, picture. And then it will make sense what this parameter pi is and why it's relevant. Because picture is very simple. So so here picture was the complete bipartite graph. This was the best construction. Here it's essentially the following. So you instead of splitting into two parts, you split into several parts. Okay, and again you put edges between the parts, but not within the parts. So this is some n over k, or approximate number of parts. And how many parts are there? Well, the more parts you take, the more edges there are. So you're going to take as many parts as you can. And how many parts can you take? Well, one fewer than the chromatic number, which is to say you want so many that the graph f doesn't embed inside. So for example, and so if for example some graph embedded into say tripartite graph like this, then you could just then you could assign to each of the vertices of the graph one of three colors: red, green, blue, say. And so the edges, so the edges between different parts, so all the edges go between differently colored vertices. So that's what the meaning of chromatic number. This is the largest number of parts for which picture like this does not contain a copy of f. Okay, and again, there's a lower order term because again, if f is depending on what f is, you can put a little few edges here and there. I don't want to discuss that right now, except to note that if chromatic number is 2, that this is vanishes. This is 1 over 1. This vanishes, and the only thing we left is the statement the number of edges is subquadratic. Okay, so let me just write if f is bipartite. So bipartite means it's quadratic numbers 2, or it means that we can just split the vertices into two classes. All edges go between those two classes. Then we don't have a true asymptotic. We only have this from this very general result. And so it's an open problem in general. It's a problem I'm talking in this talk to understand what this is like for different.
I'm a bit confused because so you stated this as though this is the asymptotics, but the example you gave before says that it's not.
In what sense? This example?
Yeah.
This.
No, it works.
How does it work?
I checked it.
Sure. This is a file. And you choose to right? So, and this does agree with this.
Sorry, chi is 2.
Chi is 3.
Chi is 3.
Oh.
Chi is 3 here.
Okay.
So, for example, so if you go to the example of chi equals 2, this for cycle, that has chromatic number 2. Because I can color this red, this blue, this red, this blue. Okay, it is bipartite graph. So the fourth cycle is harder, well, in some sense than the triangle. Yes.
When you're specifying this O of 1 term, it's still multiplicative to the n over 2. What is the dependence of O of 1 on n and f?
Okay, so all this symptotics I remember we're going to write in this course, this lecture, is as n goes to infinity, everything else being fixed. Okay, so I mean, if you're able to know what's the best known bounds here, maybe after the talk. It's probably the best way to answer this.
So, for example, this doesn't give a very strong upper bound because O of 1 could just
Okay. let me, okay. In short, okay, if for graphs which are not bipartite, the behavior of this thing is somewhat similar. You get similar problems to the case where I'm understanding this term of graph is bipartite, except they're more complicated problems. Okay, so it's kind of what you're going to see, just more complicated and even less understood. Okay, so that's kind of short answer. Okay. Okay, so let's look at some bipartite graphs and see what's now. So 4 cycles is definitely the simplest non-trivial bipartite graph. I probably should mention the case when the graph has no forbidden graph has no cycles. It's a tree or a forest. It's a trivial. Let me just try to say. I don't want to prove anything about this, but believe me, it's a trivial case. If f is a tree, no cycles, then this is linear. It's linear and fairly well understood. Even the constant here is relatively well understood. Again, and okay, this is not what I want to discuss right now. It's kind of very degenerate case. So 4 cycles is the simplest. So what's the answer for the 4 cycle? It is known. It's on the order of n to the power 3 halves. Again, actually more is known, but I want to write it in that form, not to bore you with the log order terms.
Which is a little lower than squared.
Of course, this is a little lower than squared. No. Okay. Okay, as we know it's actually okay. What I'm writing is much less precise than we know. So because what I'm writing it's bigger than some constant multiple of n power 3 halves, and it's bigger than possibly different constant multiple of n power 3 halves.
Right.
In this, guess what this notation means. In this particular case of the 4 cycle, we actually do know what this constant. This constant is the same, and we know that it's a half. And we even have some estimates on the second order term, and etc., etc., etc. But for what story I want to tell, I want to leave it in this form, not to worry too much about this constant. Okay. Now I want to tell you, just to basically give you a sense like where the problems are. How do you prove something like this? What does it look like? Why do you prove upper bound? What the construction looks like? Again, it's a colloquium talk, so I will commit certain sins of disregard. Okay. The first sin I will commit is I pretend that all graphs are regular. So I will basically for all the talks. Okay, this is I'll assume that all graphs are regular. This is Green's loss of generality.
Can you remind us what regular is?
Yes, I will. So that means every vortex has the same degree. Has the same degree, which is adjacent to the same number of neighbors. Same degree means same number of neighbors. That's what it's saying. What degree is. So, and let's say dB that degree. So, for example, again what I don't want, I want basically if I pretend I'm a vortex and I look around at whom I'm adjacent to, it looks the same number of things.
Can you comment on the generalization if you have bipartite but not K-rated?
I mean, the technicalities. I mean, basically, you just need to depending on what happens, you might need an extra Cauchy-Schwarz inequality or two, and things like this. So it's, again, some technicalities get more technical than others, but it's technicality for what I'm going to tell you. And it'll help me to convey my message across. So let's pretend that. So how do we going to prove that the upper bound? Okay. So to prove that, I'm taking my graph G of degree D. So again, that means every vertex has D neighbors, and then I will pick a vertex. So pick V any vertex, like so. I'm going to look at its neighbors. There are D neighbors. Okay, this is a set of neighbors, and I'm not going to look at the neighbors of neighbors. Okay, and the key point here that the picture I drew is correct. I'm not actually cheating you. The neighbor and the different neighbors of neighbors are distinct. So in other words, I'm not actually getting a picture like this, because if
Should have drawn two out.
huh?
Yeah, you should draw two lines if it's regular.
Thank you. No, it's good when the audience pays attention. So picture doesn't look like this, because then it would be a four cycle. This point, this point, this point. Right. So really all the this really looks like a tree. I mean, there's no cycles, and so I'm getting here D times D minus 1 vortices on the second layer, and since a total I have n vortices, this better be equal less than n. So my degree is, I don't want to write anything super precise. It's at most approximately square root n. And degree is at most square root n. Therefore, total number of edges is at most n power 3/2 for each vertex graph. Square root of n neighbors. Okay, you need to divide by 2, but no. So that's the upper bound.
But actually, some of the neighbors of V could be connected to each other. You could have triangles, right?
Oh yeah. Very good. I was trying to be. Yes, you can have triangles. So the simplest way to avoid this technicality is the following. Just to know the following: every graph G with some e.g. edges contains a subgraph with half the edges that is bipartite. And the way you can see this is there are several ways. The simplest is this: you assign to each of the vertices of your graph either one of the colors, red or blue, and the choice which you do is random, by flipping a fair coin. And then you just delete all the edges which go between two blue vertices or two red vertices. A given edge will survive probability at half. So if you do a random choice, on average you will delete half of the edges. So therefore there is actually a good choice. That's the kind of simplest argument. There are many ways to do that. So the point is, by losing just a factor of 2, which only will affect this constant here, which I'm not even writing, you can reduce the cases bipartite, no triangles. There are ways to do the triangles and not to lose a constant factor. So thank you. Thanks for paying attention. All right. Construction. Construction is also lots of fun. I mean, this is very simple. Construction is also very simple, but probably less obvious. So construction means I'm actually need to show prove a lower bound. Okay. The construction looks as follows. It's a bipartite graph. So 2 parts. The left part are the points of a plane of a refined field. So this 2-dimensional two-dimensional space over Fp. It doesn't have a prime, but I'll assume P is prime for simplicity. And on the right, I will take all the lines in the same plane. And my graph is just an adjacency graph. So point here, so point Q, say here, and the line L here. I will have an edge. Q is an edge. Have an edge to L if the point lies on the line. Okay. There are no force cycles because if you take 2 lines, so 2 points here, and there's at most 1 point intersecting. So you can't do 2. And the number of edges, well, every line contains p plus 1 points. So the degree is going to be p1, degree on the right is p plus 1, and this is approximately the square root of the number of vortices. Again, number on the right, and the total number of vortices is about double that. So it's really some multiple of square root of number of vortices. So that's a construction.
What's that notation, omega?
Oh, sorry, asymptotic. So that means it's bigger than some multiple. Okay, so sorry, I'm a bit too used to it. So that means there's some pulsive constant C, so that this is bigger than that. Sorry, if you think of big O as less than, a big omega is greater than.
Your point is that you can use some algebraic geometry.
Yes, I mean this is actually a point of much of what I'm going to tell you. Okay. So what's the status?
So is that true for every n? No, we only have a few primes way out.
But the primes are very dense. So if you no, they are very dense. Okay, sorry. I mean, I'm sure that people in this room would know better than I do. But for every n, there is a prime.
Oh, right. That's enough for this. Logarithm.
Right.
Okay.
7, 5. Right.
Okay.
I mean, so even Bertrand's postulate would be enough. Factor of 2 loss. I mean, if I don't care about it.
Right.
Okay. Of course, there are great problems there because, for example, we don't, if you want to know lower the terms, if you want to understand stability, is there as only construction? I mean, all this start to matter, but again, I'm giving currently a very high level. Okay. Yes. So so force cycle you've just seen. What's kind of rough state of our ignorance? It's as follows. So first of all, there are 2 kind of basic main there are 2 directions in which you can generalize a force cycle. I mean, if you want to know what's next, these are complete bipartite graphs. So complete bipartite. So notation for that which we use is KST, which means there are S vertices on one side, T vertices on the other side, and there are all possible edges between the two sides. That's the notation. So for that, the state of ignorance is as follows. So K to 2, first of all, it is a 4 cycle, right? This is where you see. In general, the upper bound I showed to you generalizes to this, and this is occasionally sharp. I will tell you a little bit about that.
The result is not symmetric?
Yeah, I guess.
It's not symmetric. Oh no! It's not symmetric in essence.
But S is less than T.
It's also true for the other direction, but you better use it with S being smaller than the other. No, but it's not symmetric, and it doesn't have. It should not be not symmetric. So what is known? The K33 is on the order of. So there's a lower bound, in other words, matching. So it's sharp for the K33, and I'll say some words about what it looks like. And generally, this is known to be tight, but not for all values of S and T. Only if T is much larger than S. Currently, the best known is this. T is bigger than approximately S factorial. Let me tell you what this looks like. Just to, so for K to 2, we took points and lines in two-dimensional space. For K33, what you do, you take again points down in three-dimensional space, and here you take unit spheres. And again, it's very easy to see why this works. So, what I need to show that if I take 3 vortices here, different vortices, they have only at most 2 common neighbors here. Well, here's the proof. You take, so imagine you are in R3 rather than F3. Take two spheres, unit spheres, they intersect in a circle, usually. This circle determines what the spheres are because it's a unit spheres, right? And then you take a third sphere, well, it intersects a circle in 2 points. So, end of the proof. And of course, if you think about like how do you do this over FP, well, if you actually try to formalize it, of course, I just do some polynomial arithmetic. So same works over FP. Again, small wrinkle there, which I'm not going to mention, but that's basically the proof. So one thing, for example, you might want to ask yourself, well, can you actually generalize it to the larger dimensions in the same way? That's a completely natural impulse. So again, you can if you're allowing, like very unbalanced ones. There is so some time back, I proved with some friends a negative result of this form. Its negative result is weak, so it basically says there is no such construction. Again, I'm not being super precise. Of K44 free graph. K443 graph over R. So again, so the construction they showed you, they were working over R as well as over FP, and it turns out they cannot generalize it to X1 over R. It doesn't tell us anything about the finite field, unfortunately. And it doesn't tell us anything about the graphs in general, because there's no a priori reason why things must look like varieties. We don't know that yet. But this we know that you cannot take a 4-dimensional space over R and do something like this. That's it. So
So it's not known, this extremal function is not known.
no, so the external function for K for 4 say, or larger things, it's open. I mean, open to the level, we don't know order of magnitude. We don't know it's under some power probably, but we don't know what the power is.
So this is saying you can't do it a certain way.
Yeah, so you cannot take, so here what we did with,
Yeah.
I don't write too much, but what we did here, we had a free space times the free space, and we had a hypersurface inside it. You cannot do that with 4 space times 4 space in a hypersurface. Actually, you cannot do it even topologically, so not algebraic. The proof is topological.
So you can't do it to prove what?
So, okay, fine, you want a formal thing. Okay, so what you cannot do is the following. You cannot have, say, R4 times R4, point X, point Y, and you put edge if some function, say polynomial, between f of x, y is 0. Okay, so if you have a graph like this, so this is an infinite graph. But you want this infinite graph to be K4 free. So such a graph always contains.
Constant. For any polynomial.
Yep.
Okay. I see. Positive state. Think of it as a positive state.
I guess you are an optimist.
Yeah. Everything is true.
Okay, and that's in relation to logic. Numbers bigger than 4. But I don't know right now.
But I mean, this type of arguments will give you the upper bound, or
No,
the
promise
lower bound?
it doesn't do anything for graphs. I mean, because there are 2 steps missing. First of all, it's about real numbers, not finite fields. Right? Constructions over finite fields and finite graphs we're talking about. And secondly, we don't know, it's still an open problem, a construction must look like this. Maybe there is a construction of graphs with many edges which doesn't contain, say, K for 4, which looks absolutely nothing like this.
No, but my question was more basic. So you try to do this construction. So I understand that it doesn't work, but if it were to work, what it would give you?
Well, if it were, I mean, the hope is that there is some construction which works over any field, for example, or large class of fields, then it just works. I mean, and this is, for example, the case for, K22, K33, KST I haven't shown, I'm not showing, I'm going to show it to you, but some version, I mean, it's, again, also some bunch of fields that you can work over. It's actually, if you increase T a little bit more, it works over any field at all.
But those things give you like a lower bound or something.
Yeah, you get an explicit example.
Yeah, it will give you specific examples. Yeah.
That always gives a lower bound.
Yeah.
Are you saying that if you have finite characteristic, that some of those polynomials will get ruled out, and you might be able to find? I mean, you did this argument over the reals,
Yeah.
but you don't need that to get your bound, right?
No, but this doesn't, unfortunately, this result doesn't tell you anything about bounds and Turan numbers. It doesn't give you neither upper bound nor lower bound. It just says in a certain way you can try to get lower bounds is not going to work.
What is the hope that if you do it over some other field?
Yeah, okay, ideally it would be nice if you would do some arguments like this to go over more general fields. And then plus some additional results, trying that the extremal graphs must look like this kind of algebraic way. That would allow you to make improvement on upper bounds. I mean, there is some work in that direction, partly by myself, but it's light years away from what we need. Really light years. Okay. So, let me mention maybe as follows. Let me mention the other generalization, then I tell you a little bit about the constructions, and probably that will be about the time. So the other class of examples, which you can generalize for cycles, just longer cycles again, longer even cycles, because again, if I take a cycle which is odd length, it would not be bipartite, so even cycles. Now the upper bound is the following. Okay, maybe I should call it different, not C, not different, whatever it was. Huh?
Never realized an even cycle was bipartite. Interesting.
So the generalization in that direction, upper bound looks like this, and it is sharp for, well, 2 we've already seen, 3 and 5. And again, it's open for every other value of k. Constructions are again algebraic. Also again, variety. I won't show them.
But I mean, are there any universal constructions for the lower bound?
So the construction is universal, but the actually I have 2 classes of constructions. But the constructions are free of appropriate cycles only for this values of k. So it's the same construction, but it just works only for this values of k.
But I mean, my question is some much worse N2 the.
I mean, lower. What's the best known lower bound?
Yeah.
So the best known lower bound. Sorry, I didn't write it down ahead of time. But general lower bound is some different constant. Okay, let's not worry about it. Okay, I don't remember this function exactly, but it looks like 2/3 over k plus some smaller terms. So again, there are some terms of the order 1 over k squared, which I don't remember. Again, it's a rational function. It's maybe 2 over 3k minus 1 or something like this. I just didn't write it down ahead of time. But it's approximately 2/3 of that. And there's also a better known bound for C14 than this general construction, which is, again, a complete mystery why it's there. But let's not talk too much about it. Yes?
Yeah. So in the other cases, when the graph was getting bigger, we could get more edges. But here, if we have like a giant cycle, let's see if we can get fewer edges.
Yeah, okay. So let me explain what upper bound looks like. So to define it is intuitive, because this is actually very intuitive. So let me show you proof. Again, proof in the same quotes sense as before. I'm assuming the graphs are regular. Of this assertion instead. Let's some constant. So the difference between this and this, here I'm forbidding not just cycle of length 2k, I forbid all the cycles of length up to 2k. So and then you'll see why this makes this number so much smaller, and then I wave my hands and explain how this to relate. Okay, so it's very similar to this. So you start at the graph, take a vortex of it, and start building a depth of search tree. To avoid the problems of counting how many things are drawn with the dots. So you look at the first neighborhood, the idea of them, you go out, you're going to get d times d minus 1, and you keep on doing it to depth k. So you end up to depth k with this many vortices. And it is going to be a tree, like before, because if any point, some of the two of the neighbors are going to be the same, then you're going to make a cycle. And since you're at the depth k, your cycle will have like length at most 2k. Okay? And this must be less than n. and there you go, you get into a bound of D, and okay. So this is the upper bound. Now what happens if you forbid only the longest cycle? It's just, okay, it's not trivial, it's far from trivial, but it's a technicality. It's like, how I run my living, by dealing with those things. What happens is that you need to start worrying what happens if this, say, second layer of that doesn't grow by factor of D, it grows by smaller factor. Well, there'll be many edges back, and then you start being able to make a cycle by going a zigzag and back. It's not a trivial argument, but it's an argument, and you can make it. And that will show that, okay, it will grow by a factor of L minus D, and what you get out of it. So, is the following. So if here, for example, if you think about it, I'm really showing it, actually this less than some absolute constant thing. This is really like some constant, because this constant is independent of, this constant is independent here of k. If you try to do some arguments, what you're going to get for this constant alpha k, you're going to get alpha k. Okay, in a simple argument, you're going to get this. And this is an Ordish, unpublished, Shimonovich, Pekurka, Verstrace, a bunch of people proving bounds of this form. The best current record is the square root of k log k. This is myself and my former grad student Zhang, Ziling Zhang. And this is essentially tight in the sense that, okay, here's a great problem. We don't know this is sharp. This is open if sharp. This is trivial bound, you just saw it. This is non-totally sharp. So if you improve this bound, you improve this bound. And this is trivial bound. And this is budget technicalities. So basically we got to the point basically to improve on the cycle problem, we need to actually improve something much more fundamental. And we don't know how to, we don't have an idea. Okay, that's how much time I've got?
13 minutes.
13. Oh, that's a lot. Okay, so let me tell you, if you were...
Can I have a chat?
Of course.
So what kind of graphs are you aiming to compute this thing, or what estimate? Or?
So again, it's a bit of, as I mentioned, this is a bit of a kind of, there are a few cases where this problem arises. Mostly we're talking about clicks and cycles. So again, that would be useful for some few applications. But the main thing is that again, there are generalizations of this problem to other structures of the graphs. The basic tools remain unchanged. I mean, and just more extra complexities. So we want to understand this so we can tackle those other things. So there are hypergraphs, there are directed graphs, there are tournaments, there are geometric settings, for example. Like there are quite a few cases where we do things like this, just with more ambient structure around. So that's partly why we want to understand that. Also, it's a kind of pretty problem in its own cases, but again, depends on your taste.
Is it known for like a Peterson graph or what's the name?
Peterson?
Yeah.
Peterson is not bipartite.
Oh, I see.
Can you give an example for graphs that are bipartite, but let's say have several different degrees, vertex degrees?
No. So my assumption is really more importance of the assumption of regularity is not the graph I'm forbidding, but the graph which I'm looking at G. So this is basically this allows me to actually like do the Brook issues like this without worrying that some of the vertices give more neighbors than others. And it can be fixed with simple Cauchy-Schwarz type arguments. And for example, not hard. All right. So I do want to tell you a few words about construction. So again, so all the known constructions I mentioned that are very algebraic construction, count varieties. So let me show you, for example, why result like this is true. So except that it will be different bound, not factorial, and I want to write it down. So, for example, having the construction of KST-free graphs with T much larger than S look like. So what we're going to do, we're going to do as before, FPS, FPS, and we're going to put define edges via some polynomial. And the only thing we need to do is to choose this polynomial cleverly. Unfortunately, we're not very clever. What we're going to do, we're going to choose our polynomial f at random. So the really good construction, decent construction, is to choose a random polynomial f. When I say random, I'm just going to choose among all polynomials of some degree. What's happening here? To see whether this contains a complete subgraph with S vertices on one side and T on the other, what do you need to do? You're going to look at some S vertices on the left. So this is S2, XS, and you're going to ask yourself, is the vertex, how many vertices are adjacent to all of them? That's just a system of polynomial equations. So that's just intersection of some bunch of hypersurfaces, in other words. So so what we're interested in is in the set looking like this. Know how many points there are. So intersecting S hypersurfaces in dimension S, we generally expect this to be zero-dimensional. And Bizou tells us that this, if it's zero-dimensional, is at most private of the degrees. So we expect this, if all is well, to be to have size at most due to the S. So if it's at this, if it's zero-dimensional, and point is if degree is large enough, it is going to be generically zero-dimensional. If you are probabilistic, you could think of it. There's more and more randomness. If you say, how should I say? Let me say it this way: if every function is a polynomial of degree p minus 1 for finite fields. So if you actually lower the polynomial, you still have enough independence. So if you have degree d, your variables are going to be d-wise independent. If you take d large enough, all the quantities you care about, you can still estimate all the moments, for example. So this is a kind of very high level of argument how this works. So if you take d large, approximately like 2s, this is going to work. And you're going to get a construction where your t is something on the total magnitude. So it's like slightly more than factorial, not that much. So with this kind of games, one can prove some results. For example, here is, for example, a relatively recent thing which we proved in another colleague of mine. For example, for every rational number alpha between 1 and 2, we can construct a family of graphs. Graph family, such that the extreme of function for which all of them is that the alpha. Again, by playing this kind of games, we don't. So this is approximately kind of the state of the art. So we have on one hand we have these algebraic constructions, which are either some special kind of varieties, which you need to be lucky to find them, or this kind of random algebraic constructions, which you don't need to be lucky, but they're not as good. Upper bounds, again, they're basically these very simple arguments, which is just taking order to draw things. And again, except you need to worry about degeneracies, and then it starts getting complicated and fun. And that's approximately where we are. And I think it's about my time, if I'm not mistaken. I'm happy to answer more questions you might have. And thank you.
These equations mean?
I
didn't follow how you use those.
Sorry?
I didn't follow how you use those.
Okay, so so if I take a S versus on the left of the graph, on the right, I want to know what the versus of common neighbors of them. So this is maybe a bit of shorthand. Maybe that's the problem. So this is written fully. This is the set of all the y's. Sorry for the shorthand.
Okay.
This was this. Okay. Right, this is the set of all the common neighbors. So, I think there was a first hand there.
Do you always get fractional powers?
Open. That's open. We don't even know that it's going to oscillate up and down. That's all we know.
Looking at the Erdős bound that you wrote before, the chromatic number of a graph is the smallest size of a graph, such that your original graph has a graph homomorphism that surjects onto that. And similarly, all bipartite graphs which aren't a discrete set of vertices are exactly graphs which have a surjective graph homomorphism onto the line. Is there a property preserved under graph homomorphisms of Turan
Well, you
problems?
want to basically say some kind of conjecture about how this behaves. It's just behaves nicely in the graph homomorphism.
Surjective graph homomorphisms.
Look, I mean, we don't have any idea what this looks like. I mean, my current best guess, I mean that, let's say, if you look at the question, I give you a graph G, and you tell me what this exponent is, or assuming this exponent, my best guess should be undecidable. Okay? In particular, so that's my best guess. Particularly, you should not expect anything super nice. But sometimes all the results we have are a bit positive direction. You can prove something which is nice, etc. And the reason I'm so pessimistic is, well, it's usually things are decidable. And secondly, you get this kind of redestructured like variety and so forth. You should be able to code things up into that. I don't have a way of doing it yet.
So there are no results that actually write graph homomorphism into this wrong. Okay, interesting.
No, sorry, I was asking why the question. Yes.
So in some of your examples, you realize the set of edges of your graph as the algebraic variety?
And all examples, really.
And is there a way of translating your problem into the topology problem, or if you define it?
No, so again, so the topological thing was what I'm looking for. We assume that your ground fields are and that your structure is like this. It's a topological problem. That's what we did exactly. It's a topological result. You don't have a translating results for graphs in general. So that, my best guess, you need to prove some cross results, and the best construction must look like this, and then do that. But we are far along with it. Not far, haven't gone far along with it. No. I mean, actually more, sorry for interrupting you. Is even more. The constructions for the cycles, which I haven't shown you at all, the best constructions, they have a strong the algebra flavor, very strong. But it's not, we don't have a systematic explanation for that.
Which is the result for a tree?
Sorry?
Which is the result for trees?
For trees, okay, this is the general case. Okay, so tree result is actually really easy. Okay, first of all, and the approximation number 0, if you assume that your graphs are all regular, degree D, which is what we've been doing so far, then it's very easy to embed any tree. I first have some tree T, I pick some vertex of a tree, I put it somewhere in my graph. I want to, this vertex in T has a neighbor. Well, I'm picking from the neighbor of this vertex. Just put it in. This one has some neighbors, I just put it in. And point is, as long as it picks fewer than D vertices, and if I want this vertex to embed some neighbor of it, there's still this D vertex which among its D neighbors, at least one of them has not been used. I can just use that. So finding a copy of a tree is really easy. So that way you're going to get a bound. So if your tree has tree T has m vertices, you're going to get a bound at T, which is okay, n times m. Just by this trivial argument, okay, you will get it within a factor of 2 of optimal if you just do exactly what I say. That's the stupidest thing you can do. If you want to get a sharp thing to double within a factor of 2, that's where some difficulties begin. But, okay.
And the results of this problem you apply to the problem with unfixed numbers of points?
Base numbers.
Unfixed numbers of points. So you might have more, the number of points is not fixed. But you have to assume that it's enough edges. And you still don't want the embedded forbidden graph.
I'm not sure. Are you doing geometric problems? You're doing geometric problems, so I'm not necessarily with 4 points.
You don't fix the number of points.
You
can just keep adding.
Oh, you're talking about, if you don't restrict my graph to have n vertices.
What?
You don't restrict n.
So you don't restrict n.
Yeah. We don't restrict n.
Well, then of course, then basically you're asking for maximum of this overall n, right? This is what you're saying.
Maybe it's going to be the generated function that will be more easy to find.
Sorry?
The parameter there, raised to the power n, sum over n. Generated function.
Wait, so are you asking, how this behaves as a function n is, maybe, I was like, nice formulas for this are highly unlikely to exist because, again, I can remember this construction. We know that for 4 cycles, as an example, we know that the version of the construction I showed you with some embellishments is actually optimal, like literally optimal. So it means, but if you make it number 1 less than the prime, it's not going to exist. So it's strictly not good. So for prime values, it's going to be some polynomial. For things which aren't prime values, it's going to be something else. We don't know what, but it's something else. Expect that the generating function will be nice in that situation is too much.
Right, let's thank Boris again.